Good evening, Professor. My name is Philly. I'm from Civil Engineering Department. This is my term project, M132-Calculus 2. So I'm responsible Chapter 10, Infinite Sequence and Series, and Section 10.6, Alternating Series, Absolute and Conditional Converge. So this is my content. So let's start with introduction. So alternating series is a series in which the term alternately positive and negative. So which means that this series start with negative or positive rapidly. So here is the form. The sum of n's equal 1 to the infinity minus 1 to the n u sub n. So the alternating series test. So the theorem 14, the alternating series test, the sum of n's equal 1 to the infinity minus 1 to the n plus 1, u sub n's equal to u sub 1 minus u sub 2 plus u sub 3 minus u sub 4 plus so on. So convergence is if all three of following conditions are satisfied. So the first condition is u sub n's are all positive. Second, the positive u sub n's eventually is non-increasing, which means that it is decreasing as u sub n's greater or equal to u sub n plus 1. So for all n's greater or equal to capital N, for some integer capital N's. So the last condition is the limit n's to infinity u sub n's must be equal to 0. So let's prove for the first part, which is u sub n plus 1 less or equal to u sub n. It is a decreasing series. So the sum of 2 equal to u sub 1 minus u sub 2 greater or equal to 0. And let's start with the same until the s sub 2n's equal to s sub 2n's minus 2 plus u sub n minus 1 minus u sub 2n's greater or equal to u sub 2n minus 2. So in this case, we can conclude that u sub 1 greater or equal to u sub 2 greater or equal to u sub 3 and greater or equal to u sub 4. So this is this series is true. So second is the convergent series must be approached to some definite number, which means is S. So let's start with the limits n to infinity as sub 2n plus 1 equal to the limit as sub 2n plus the limit as sub b sub 2n plus 1. So the limit as sub 2n is equal to s, and the limit as sub b sub 2n plus 1 is equal to 0. So this proof is equal to s. It is true. So let's take a look at an example. The sum of n's equal 1 to the infinity minus 1 to the n plus 1 over n's. So let's substitute the three conditions. So the limits n to infinity 1 over n is equal to 0, which means pass the test. And the second is this series is a decreasing series. So since all of these pass all of the step of the test, so it is convergent. So let's take a look at another example. The sum of n is equal 1 to infinity minus 1 to the n plus 1 by n plus 3 to n over 2n minus 7. So start with the limits u sub n. In this case, the u sub n 5 plus 3 over 2 minus 1 is equal to 5 over 2. So it is not met the condition. So it is fail the alternating series test because the limit of u sub n is not equal to 0. So the series is divergent. So the alternating series estimation theorem. So theorem 15, the alternating series estimation theorem. So if the alternating series, the sum of n is equal to 1 to infinity minus 1 to the n plus 1, u sub n satisfy the three conditions, then for n greater or equal to capital N. So S sub n equal to u sub 1 minus u sub 2 plus dot 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 plus minus 1 to the n plus 1 u sub n. So approximate the sum of L of the series with an error whose absolute value less than u sub n plus 1. So the absolute value of the first unused term. Furthermore, the sum of L's lie between any two successive partial sum S sub n and S sub n plus 1, and the remainder L minus S sub n has the same sign as the first unused term. So this is the estimation theorem, the form of estimation theorem, and which means that to this theorem is to estimate the sum of alternating series to desire the amount of accuracy. So let's take a look at an example. So the sum of n equal 1 to infinity minus 1 to the n plus 1 over n squared. So first we need to test the three conditions of the theorem 14, the alternating series test. So the limit is the limit n to infinity 1 over n squared is equal to 0, and this is the decreasing series, so it is convergent. So let's start with the alternating series test. So the absolute s minus s sub n equal to absolute remainder or less than or equal to u sub n plus 1. So let's set the remainder. So let's set the remainders equal to 0, 0, 1. So in this case, we need to find the n. So now n is equal to 31. So the sum of 31 is equal to 0 0.82, 29, and 71. And as 100, the sum of 100 is equal to 0 0.82, 24, and 175. So in this case, we set two decimal place. So s equal to 0 0.82. So absolute and conditional converge. So the definitions, a series, the sum of a sub n converge absolutely if the corresponding series of converge absolute value, the sum of absolute a sub n converge. So for example, the sum of n equal to 0 to infinity 1 over n, 1 over 2 power to the power of n. So in this case, it's both absolute and the original series is converged. So this call is converged absolutely. And a series that converge but does not converge absolutely, it is converged conditionally, which means that one is converged but the other is not. The second or the absolute is not converged, so it is called converged conditionally. So the absolute convergence test. So theorem 16, the absolute convergence test, if the sum of n's equal 1 to the infinity absolute a sub n convergent, then the sum of n's equal 1 to infinity a sub n convergent. So this is the proof. Suppose that the real number is in the middle, and left is the negative term and the right is the positive term. So we check the negative term move to the right and equal to uh, a sub n plus absolute a sub n and less than or equal to 2 a sub n to absolute a sub n. So the sum of n is equal 1 to infinity a sub n plus a absolute a sub n less than or equal to the absolute n equals 1 to infinity to absolute a sub n. So in this case, we can compare that by comparison test. So the sum of a sub absolute a sub n is convergent, but this is multiplied by 2, so it is approach to infinity. So this is diverge, and this is smaller than the 2 of absolute a sub n is convergent. So let's subtract this original term. So when we subtract here, this equal to the sum of n equal 1 to infinity a sub n. So this is true. So let's have a look at an example right here. So the sum of n equal 1 to infinity minus 1 to the n plus 1 over n squared. So this is a converge absolutely, because the original term and the second term is both are converge. And b is the sum of n equal 1 to infinity minus 1 to the n minus 1 and to the power of p. So it is converge. So if p is greater than 0, so if p is greater than 1, the series converge absolutely. But if the p is greater than 0 and less than or equal to 1, the series is converge conditionally. So the last part is the rearranged theorems for absolutely convergent series. So theorem 17, the rearrangement theorems for absolutely convergent series. If the sum of n's equal 1 to the infinity a sub n's converge absolutely, and b sub 1, b sub 2, b sub n's is any arrangement of the sequence a sub n, then the b sub n's converge absolutely, and which means that the sum of b sub n's equal to the sum of a sub n. So in this theorem, which means they focus on only absolutely convergent. So when we rearrange the absolute convergence, so it's still result in the same result. But if we rearrange the conditional convergence, we will get the different result. So for example, right here, so the sums n equal 1 to the infinity minus 1 to the n plus 1 over n. So we know that the series is convergent to some L, and we try to multiply by 2L. So the L which we represent by this series, so we multiply by 2L is equal to the sum of this, and we group this pair of the same denominator and leave negative term. So this equal to turn to like this series turn to original term. So because of this series is convergent conditionally, so it's become to harmonic alternating harmonic series itself. So it would be implied that the 2L equal to L, which is false in L is not equal to 0. So this shows that the conditional convergent series cannot rearrange to expect the new series to be the same as all of my topic. Thank you for watching.